Yes, wait, I hope I pronounced that correctly.
Close enough.
Close enough. From the University of Washington. He's been, I finished a graduate work from the University of Kentucky many years ago now, before moving to Princeton, where he was one of, really I would call him one of the builders of the Sloan Digital Sky Survey, working originally with Robert Upton there, and then staying on his prestigious Russell Fellowship, doing a lot of groundbreaking work with the Sloan Digital Sky Survey, before he moved to join the faculty at the University of Washington, where now he's decided the Sloan Digital Sky Survey was just the first step toward what you might want to do. And so today he'll be telling us about the Large Synoptic Survey Telescope, which of course will make Sloan look like we were all just a bunch of idiots. So it's a great pleasure to have you here today.
Thank you. Thank you for inviting me. Never been here, and so far it's great.
Curious about.
10 seconds ago, I was reminded of my first day as foreign grad student doing my first teaching. And I come to class, and there is a guy with big blue beard, and I'm totally puzzled what's going on. But I didn't know how to react, so I just ignored it. But this time I'm not going to pass on it. There is a guy with a big beard. Okay, now that I got this off the chest. So I will be talking about astronomical surveys, but I'm not going to do a survey of surveys. I'm going to mention only two surveys. One is LSST, and because it's always dry to talk about future surveys that don't have data, I will use SDSS as example of what you can do with surveys, and I will also use it to extrapolate performance of SDSS to level of LSST, so that you can get a rough idea what to expect from LSST. I will not mention great surveys that are ongoing, like for example Dark Energy Survey or Pan-STARRS that are doing great stuff, and they're somewhere in between SDSS and LSST. I will just focus on Sloan and LSST in the interest of time. This is not a statement that Dark Energy Survey and Pan-STARRS are not worthy of whole colloquium or super interesting. So I will start with, it's a little bit cut off.
It's our projector.
Okay.
We can actually see it.
That's fine, it's not a big deal, it says overview. So I will start with a short overview of LSST science drivers, and I will briefly describe the system as it is designed now. I will spend most of my time going through some examples of LSST science that we will be doing one day. And then at the end, I'll just spend a few slides on a shameless advertisement, and you will see what I mean at the end of the talk. So there were four main science themes that we used to design LSST. This is not a statement that we only care about this kind of science, or that LSST will only do that type of science. It was simply four sets of science projects that helped us quantitatively design the system and tell engineers what do we want to have at the end of the project. And this science is described in about 600 pages in this book called LSST Science Book. We call it affectionately 100 PhD theses, because there were 10 science collaborations separated by type of science, and then we said to each, write description of first 10 PhD theses you will do with this data. That's why it's called 100 PhD theses. And you can find there technical information about LSST, and you can also find all these science projects. Of course, it's not complete, and we'll be doing many other things. When you go through, okay, this one is important statement that is missing. It says about 90% of time will be spent on a uniform survey. When you go through all these 100 or more science examples and you ask what kind of data I would like to have from this system, you find out that you could deliver a single data set and accomplish all these science goals. This is very important. This multitasking is why LSST will be so efficient as a survey. There will be no time allocation committee that will chop the time into small parts. A single data set will serve all these projects. So you can think of it, if you have 100 projects, like if you had 100 LSSTs designed for each individual project. And so most of time will be spent on uniform survey that will observe the sky in few nights and then do it again and again and again, and over 10 years it will do so about 1,000 times. That's why we called it LSST is a digital color movie of the universe. As opposed to SDSS, that was a snapshot of the sky. In most of the sky covered by Sloan, you get one Sloan observation. Here you will have 1,000 observations, you will open time domain. So So the shortest description of LSST that I can come up with is this one statement, that it will be optical near-infrared survey of the sky in 6 bands going from U to Y, so from 0.3 to 1.1 micron. It will go to R of 27.5, which is roughly 100 times fainter than Sloan limit. And it will get to this depth by obtaining 1,000 observations over a 10-year period. So it will be long time scale, time domain for faint sky. And if that book of 600 pages sounds intimidating, this AstroPH paper has only 30 pages, and you can find out all the relevant information about LSST from the technical point of view, as well as science programs that we aim to accomplish. So this is much shorter version.
Zeljko, what's that little telescope in the background?
This is our auxiliary telescope for doing photometric calibration. So it will observe bright stars with a spectrograph at the time the big telescope is doing imaging. And then by comparing the spectrum that we get from this telescope at that time to the intrinsic spectrum of the star we are looking at, we will get atmospheric transmission. And then this atmospheric transmission will be used to calibrate data from imaging. So instead of having K coefficients, if you ever did optical survey, optical data reduction, where you have atmospheric K coefficients, which are linear relations with air mass, here it will be done directly without fitting anything as a function of air mass. It will be simply throughput of the atmosphere at that time in that direction.
That's the way Sloan worked, right?
No, Sloan didn't have spectrographs. Sloan had,
Oh, camera.
yeah, Sloan had broadband imaging. So with Sloan, you can get great broadband photometry, but for example, if you have supernovae with narrow lines, you shift them slightly, photometry can change by a few hundredths of a magnitude, but you don't know it if you shift them in redshift. So that's one advantage over SDSS from LSST. In slightly more technical detail, what will the data set look like? We will observe the sky in one night about 5,000 square degrees twice with delta T of the order 1 hour, and this is to catch moving objects because asteroids are both scientifically interesting. There are also, as Sandich called them, vermins of the sky. They would contaminate transient samples, so we want to find them reliably. So that's why we get 2 observations per night. And it takes about 4 nights on average to cover the whole sky, and then we do it again. And 90% of time will be spent on these observations. At the end, we'll have about 100 petabytes of data, and they will result in measurements for about 40 billion objects. That will be first time in history that astronomers will have cataloged more objects than there are living people on Earth. It never happened before. And the coverage will be mostly in southern hemisphere. This is 8 of projection of equatorial coordinates. This is celestial equator. This is galactic plane. This is ecliptic, this line. So there will be main survey area of 18,000 square degrees, observed about in this band, R band, about 200 times. And then we'll also fill the area around South Pole, galactic plane, and this is added to increase completeness of moving objects. Another way to demonstrate what will be the difference between LSST and Sloan is just by images. If we can just dim the lights slightly, that would help. So this is 3 by 3 arc minute stamped from Sloan color composite GRI. You can see a bunch of galaxies, some stars, and this is the same part of the sky, same scale, from deep lens survey, which is almost as deep as LSST. Not quite, but almost. Okay, looks much better, thanks. And now you can see what you get with deeper data. First of all, if you look at this dark region, there is many more sources. That's why LSST will have 40 billion sources compared to Sloan less than 1 billion. And then also if you look at the individual objects, you can see the effect of surface brightness limit. These galaxies that look pretty boring in SDSS, you bring out a lot of structure in the outer parts of these galaxies. That's due to fainter surface brightness limit. And then seeing will be also much better, factor of 2. This is image of a lensed quasar that is not resolved in Sloan. It was recognized using colors. And this is image from Subaru telescope that has 0.7 arcsecond seeing that is roughly like LSST. You can clearly see 2 point sources. This is just an illustration of what factor of 2 in resolution can bring you, in addition of going deeper. And then, of course, it's huge amount of data. When Sloan started, we used to point out that the amount of data collected by Sloan is as much as US Library of Congress, which is gold standard in libraries. But now with LSST, we get 1 Sloan per night, so it's not impressive anymore to compare it to the Library of Congress. But when you add up all this data, roughly 100 petabytes, it turns out that this is equal to the volume of all the printed material since Gutenberg to today. All newspapers, books, everything in all the countries of the world. So that's what 100 petabytes is. So how do you get such an impressive data set? What do you need to have? Well, in order to go faint in short time, you need to have large mirror, large correcting area. So you need at least, roughly speaking, 6-meter collecting area. Then you also need to have large field of view. If you have small field of view, then you cannot cover the whole sky quickly enough. Once you have large field of view, and LSST will have 10 square degree field of view, and if you want to Nyquist sample in atmospheric seeing, you immediately realize you have many billions of pixels, and indeed, we will have 3 gigapixels in LSST camera. And once you make exposures with 3000 megapixel camera every 15 seconds, then obviously you have huge data rate, and you need sophisticated software to handle this data rate and to do precise measurements that you need to enable for astrophysical studies. So let me now quickly take you through a few pretty pictures of the design for the 3 main components of the system. So this is design of telescope. It looks like spaceship, or I saw a picture where people compare it to Sphinx from Egypt. And this is basically because the wind blows from right to left in these pictures, and this is to improve seeing. So it's slightly now off scale. It's very short telescope, basically because we want to enable fast slew and settle. It should slew to next field in 5 seconds and start new exposure. The main distinguishing characteristic of this telescope is not its mirror size. It's substantial, but still not among the largest telescopes. The main reason why LSST will be such a different instrument is the field of view. And this compares the field of view Gemini South, that has similar mirror as LSST, even more effective area than LSST. But the big difference is in field of view. This is field of view of Gemini, and this is field of view of LSST. Obviously, if you can cover sky with this field of view, you can do it much faster than with a small one. And that's the main secret of LSST. You achieve this large field of view by having unique optics, so-called Paul Baker system, where when photons come in, they bounce off the outer edge of this mirror. This is primary mirror, this annulus, but not the inner part. Then they go to secondary mirror, bounce back to inner part of this structure, which is tertiary mirror. It has different figure. And then it's focused in 3 refractive elements, and then the camera sits in here. And because of this 3-mirror design, you can maintain high image quality while having large field of view. If you didn't have this design, image quality would be insufficient. Think?
So since the secondary has 3.4 meter, what is the effective diameter for this LSST?
6.3 meters, when all the losses are taken into account.
Okay.
And we already have these mirrors thanks to generous donations from Bill Gates and Charles Simoni. This is after casting the mirror at the Mirror Lab in Fjord Observatory. You can see now it's being polished, this outer part, this part of the cast. This was done by spin casting. And this inner part, which has different figure, has to be polished out. And this is now just about done at the Mirror Lab.
So it's one mirror, just with different...
It's one solid piece of glass, but it has 2 different figures. The outer one coming from rotation while it's still melted, and the inner part essentially it's dug out. This is design of the camera, so photons come from left to right. You can see the focal plane. Here will be filter exchanger, and it's fairly large camera. It will be the largest camera for astronomical purpose built in the world. Here is the focal plane that shows how you can get to 3 gigapixel. So each of these big red squares is shown in here. It's called raft. It's essentially a single camera. It has its own electronics in here, and they can be replaced. If one is dead, you can replace it with another one. Within this each raft, there are 9 CCDs. Each one is 4K by 4K CCD. So there are 9 of them. And when you add it all together, that's how you get to 3 gigapixels. The data stream will start at the summit, and then it will go to base site, where we will do nightly processing. Basically, each new image that comes in will be subtracted from co-edit image of static sky that will be collected during commissioning. And then once you subtract these two images and you get difference image, you look for objects in difference image, measure their properties, and you feed it to public data stream within 60 seconds. And because it has to be done in this short amount of time, this processing is done at base site. And then data is shipped to continental US, and there will be a couple of data centers or one data center in continental US that will do daytime processing and also yearly data release processing, just like SDSS. There is only one line in here, so usually I put this slide too, to prevent questions about redundancy and danger of breaking this. There are many fibers, it's just that symbolically you show one. And then software is something to worry about. So there will be 100 petabytes of data. This is basically one SDSS per night that we have to keep up with. It will be very complex data set. There will be 1,000 measurements, where each measurement means of the order 10 to 20 numbers per object. There will be 60 columns in database, but if you look at the independent numbers that are of the order 10, you measure these 10 numbers 1,000 times, and you do so for 40 billion objects. So it's a very hard problem to attack, and especially when it has to be robust and done in essentially real time. So we are writing lots of new software. We are trying to recycle as much as we can, but we're also writing lots of new stuff. There will be of the order 10 million lines of code at the end. We are using C++ for primitives and Python for gluing everything. And now we have of the order 30 people working on it, and once we go into federal construction, it will be about 100 people working on software for the next 5 years or so. So that's short summary about the system itself, about the design and what to expect. Now I will go back to the science mode and show a few examples of science that one could do. Of course, I cannot touch on everything. As you saw, there are 100 PhD theses even after rudimentary thinking about the data set. So I will just highlight some conceptual things that we will be doing with these data. So to begin with, we have cosmology that is one of the main science drivers for LSST. There are 5 modern ways to measure cosmological parameters. 4 of them you can do with optical data. Cosmic microwave background, of course, you need microwave data. But these 4 that you can do with optical, we will attempt to do with LSST. We will do with LSST, and that basically comes down to measuring 2 functions. 2 functions as a function of redshift. So one is Hubble constant as a function of redshift, and the other one is growth of structure function as a function of redshift. These 2 will give us cosmological constraints, and we expect that we will have measurements of cosmological parameters of the order 1% or so. These measurements will be derived from our gold sample of 4 billion galaxies. There will be about 20 billion galaxies in sample, but these are high signal to noise that will have redshift precision required to do cosmology. And it all comes down to how well you can measure co-moving distance. So this axis is relative error in co-moving distance. And this is the range over which we can measure it. And these individual points show basically eigenmodes, which modes we can independently constrain. So for example, if you think of equation of state for cosmology, for dark energy, we are not just fitting 2 numbers. We are not just fitting one slope and normalization. This is basically the number of parameters we could fit if the real equation of state is really that complex. But we'll be able to resolve about 10 eigenmodes. And this purple line is basically what one should remember. It's 1% precision. Today, we can already reach 1% precision. For example, with BOSS survey, there is 1 point in here, and then 1 point roughly around redshift of 2. This is just 2 eigenmodes, but we can do 10 eigenmodes with LSST, and in this significant redshift range, where a lot of cosmological and galaxy evolution changes happen. In addition to galaxies, we'll also have supernovae. There will be millions of supernovae, and hundreds of thousands will have excellent light curves for doing cosmology. And one distinguishing characteristic of supernovae is that even one object is a cosmological measurement. With all these other measurements, like baryon acoustic oscillations or weak lensing, you have statistical probe. So you cannot do it with one galaxy. You need to have many galaxies and average them. With supernovae, small number of supernovae, you can already measure cosmology. So what you can do when you have this large number of supernovae is to do it in small patches on the sky and do cosmology instead of across the sky like today. Just do it in one patch of the sky. And you can roughly do it on patches of the other 100 square degrees. And you can ask whether the universe is homogeneous and isotropic, cosmologically speaking. And this is fundamental assumption that underlies everything we concluded about the universe, including the acceleration of the universe. When you derive your equations, you always assume this, and it has never been tested in practice because we couldn't do it. We didn't have data. With this supernova sample, we will be able to do so with LSST. And then, probably our best bet for getting Nobel Prize with this data set is to compare growth of structure function and Hubble constant as a function of redshift to distinguish hypotheses where the recent acceleration of the universe is due to some mysterious fluid called dark energy, and the other hypothesis that something is simply wrong with our understanding of general relativity, with behavior of gravity on large scales. So basically, if you want to put it in a newspaper article, it's, was Einstein wrong, or is there some mysterious fluid? And with this data set, we will be able to distinguish these two hypotheses. And so in addition to cosmology, with these galaxies, we will also do great galaxy formation and evolution studies. This shows the distribution of redshifts for LSST sample. There is some uncertainty because our knowledge is limited today. But the point is that these distributions, whether magenta or green, are shifted to much larger redshifts than Sloan. So this is Sloan redshift distribution. So essentially, Sloan is the snapshot of the universe as it is today. It is small redshift. With LSST, we'll push to redshifts beyond 2. We will be looking at the evolution of galaxies in essentially real time. And this is a summary of what we learned from Sloan. So this shows absolute magnitude. This is U minus R color, which is sensitive to star formation rate. So basically, you have elliptical galaxies in this mode, and you have spiral galaxies in this mode. These white contours, they show distribution of galaxies in this color magnitude diagram. Blue galaxies, red galaxies, and the background shows local density around galaxies, mean density of that magnitude and that color coded on this scale. It shows you that luminous red galaxies live in very dense regions, and in this region, the luminosity is correlated with density, and for low luminosity galaxies, it's correlated with color. And now this is our understanding from models. This is Millennium simulation, processed the same way as Sloan data, and these two look fairly similar. There is a little bit of cheating because Millennium simulation used Sloan to fine-tune the parameters. But still, it nicely summarizes, this is what we measure, this is what we interpret. The problem is that this is still snapshot at C of 0, and with LSST, instead of having two static images, we will make a movie out of this analysis. We will do it in real time as a function of redshift going back to redshift of 3 or so. That's the excitement for galaxy evolution studies. In statistical sense, it will be also interesting to look at individual galaxies, and again, this is comparison Sloan versus MUSIC survey that goes not quite to LSST depth, but almost. And this is the same region on the sky on the same scale. You can see these two objects. This is one of millions of boring galaxies in SDSS. You can describe it with a handful of numbers, luminosity, axis ratio, and so on. It doesn't have lots of structure, many details. And now if you have better data that goes to deeper surface brightness, there is big difference between this detection and this detection. Now you can clearly see these tidal streams. Now you know it's not just ordinary galaxy, but it had some disturbed history. The shapes of these tidal features give you constraint on potential around that galaxy. So it's much more rich data set than just looking at the Sloan data set. And in addition to just plain galaxies, there will be lots of data to study active galaxies, both AGNs and quasars, the luminous subset of AGNs. So in this diagram, you can see absolute magnitude as a function of redshift for quasars from Sloan, this line is the limit of spectroscopic target selection for quasars. So Sloan quasars live in this region, but quasars are formally defined to be more luminous than this limit. So there are lots of quasars in this region that SDSS did not detect. And this is where theorists tell us that you can get the strongest constraints on the models for formation and evolution of AGNs. And that's where LSST will come in. This limit is 24th magnitude, and that's the limit of single epoch LSST survey. So there will be millions of quasars that we will discover. Of course, you can immediately raise the question of spectroscopy. SDSS targeted candidates selected in imaging data for spectroscopy and then demonstrated that target selection worked fine, but still it was only 2/3 of the objects that were targeted were actually quasars. 1/3 were stars. So how will LSST do it without spectroscopy? And the answer is time domain will help. All quasars are variable, so we will look at variability, and also with time domain we will measure proper motions that Sloan didn't have. And with these proper motions we will also significantly decrease contamination by stars. We can reject stars. And so next few slides I will just show you what you can do with variability with time domain. It's based on stripe 82 from Sloan, 300 square degrees where Sloan actually did have time domain data. And first let me just briefly address how we will find high redshift quasars. This is the highest known redshift quasar from UKITS at redshift of 7. And you can see here how it will work. This will be 2 bands from LSST Z and Y, the other bands are to the left. And this quasar would be detected as a Z band dropout. You would see a point source only in Y band and nothing in UGRIZ. Of course, you know, if you ever try to do this game with SDSS, you know that what kills you is false positives. It's very hard to clean your data set from things like cosmic rays and all other artifacts that may happen in your data set. And that was very hard to do with SDSS. But here we will have many observations. It will not be just one observation in Y band, it will be hundreds. So even if it happens that in one observation you have cosmic ray, these cosmic rays will not be coherent spatially, so it will happen in one observation, but not in the others. And you will also be able to look at variability of this Y band flux and distinguish between normal stars and quasars that have very characteristic signature in variability. And then you'll also have proper motions. So brown dwarfs that will have similar colors will move over a few years by a large amount. So that's why we will be able to end up with a sample of about 1,000 quasars at redshifts beyond 7. Today there is only one known, this one on the picture. And they are extremely important objects because among other things they can be used to map the reionization distribution in the universe, both in redshift space, and when you have thousands of them you can look at homogeneity across the sky. So let me now spend few slides on variability of quasars that are at lower redshifts, below 2. So this is G minus R, U minus G diagram from Sloan, 4 point sources. These are main sequence stars, and the color coding is variability. What fraction of objects varies with RMS more than 0.05 magnitudes? 100 means 100%. Red means 100%. So what you can learn from this diagram is that in this region, and this is where quasars live, 100% of objects are variable. And in this region, where our Lyrae stars live, of course, all of them are variable. So by adding time domain, time component to your data, you can learn details about these objects that you could do with static data only if you had spectroscopy. But if you had time domain, you can bypass spectroscopy and still conclude that you're looking at quasars. And you can go one step further and ask not about variability amplitude, but also about timescales. If you had periodic star, you would then fit some harmonic and you would get periodicity, you would get period of our Lyrae star or any other periodic star. With quasars, it doesn't work because they're not periodic, so you need to be slightly smarter, and the way to do it is to treat it as a stochastic process, and in particular, this diagram shows timescale determined using damped random walk. If you never heard of it, be patient, I will show what it is on the next slide. On this slide, The point is that when you fit this damped random walk model to the data, to light curves from Sloan, for these objects and these objects, you find much longer timescales for variability of the order years, as opposed to stars that vary on timescales of the order days. So if your light curve extends many years, it's a piece of cake to distinguish stars from quasars. So what is damped random walk? You know that random walk is 1 over f squared process. And if you look at power spectrum, then overall this is frequency at the bottom, and this is power spectral density. This is 1 over r squared. So if you now make it flat here, that's called damped random walk. If you look at differential equation for generating this process, there is an extra term in that differential equation that brings the process back to the mean of that process. And that's why in PSD you have this flat thing. Or if you look at just random walk, this random walk will go away as square root of n, where n is the number of steps. Sometimes random walk is called drunk man's walk. Damped random walk could be then called merit drunk man's walk. Because whenever you go out and you drink with your buddies, you come home. That's your mean value of the position. There is differential equation term called wife that brings you home. So that's what's going on in here. And so this cannot be excluded in statistical formulation as the explanation for quasars. In other words, it fits all the data. So now when you fit such process, there are 2 parameters. There is 3. One is dummy mean magnitude. Second one is amplitude of this variability. And the third one is time scale. When you fit this, then you get these morphology diagrams. The main point to take home is that when you look at sample that has spectroscopy, the red points are stars and the blue points are quasars that you concluded by looking at their spectra. When you now forget about spectra, you just look at imaging data, and you look at your light curves fit damped random walk. This is the distribution of time scale. You pick up the same morphology. This is distribution of amplitudes. And this is parameter that shows the slope. It's derived from these 2. This one is almost like PCA component. This one looks almost identical like this diagram. So the bottom line is you do not need spectroscopy to reliably find quasars. It's sufficient to have precise time result photometry. Precise at the level of few percent or better, and it has to be on time scales of years or so.
It must be extrapolated to higher redshift. I mean, the one flare showing for quasars talks about redshift 3.5.
That's right.
So if you go higher, there must be other. It must extrapolate.
Right. There are not as many data for high redshifts. There are projects going on to demonstrate to find out if the physics is the same. I'll show a later slide. For up to redshift of 2, there is no evolution with redshift. The physics, basically, it's probably accretion disk instability, doesn't care what redshift you are looking at.
The time scales being stretched.
But time scales, then there are cosmological effects. It becomes easier as you go to higher redshift because everything contracts.
But the time scale gets shortened because of time dilation.
That's exactly why I say
So
it
it's
gets
factor
easier.
10, but then you don't have as much information on time.
Wait, it gets shorter, longer.
What?
Time dilation is longer for higher redshift.
Yeah, but the time between clicks, you'll see in the rest frame of the quasar, you'll see 1 year. So it will be a
Oh, I
short
see.
time period.
That's right, but
So-
the time scales are such that ideally you would like to have survey 10 to 20 years. 10 is minimum. Now it's time contraction. You basically then effectively have 20 years survey for high redshift quasars than for low redshift quasars. So it does help you. You are more effective. If the physics is the same, you're more effective with, it's the same as with supernovae. So you don't have to go that long. You can work on shorter stretches.
But you were arguing that it was the variability over a time period that gives you the information. The rest frame time period at high redshift is much shorter, and so you have less information about the long-term variability of at high redshift and low shift redshift. Same with supernova. And so, the supernova lasts for a lot longer. It goes up and goes down,
Right.
but you don't see as much of the light curve over a fixed time period at high redshift. So locally, you're seeing 10 years of variability of quasar. High redshift, you're seeing 1 year.
The
That's
study.
right. I reversed argument from supernovae. Yes,
Yeah.
you're right. You're right. It's not easier. You're right. Yeah, I was wrong. I had supernovae and something else in my mind.
No, it's fine.
I have a
Okay.
problem too.
Yeah. So going back to low redshift quasars, so there are no high redshift quasars in here. It's all less than 2.5 or so that's UV selection. So this shows is this time scale that you fit and amplitude essentially, and that's done now with real light curves from Sloan. And for all these objects, you do have spectroscopy, so you can measure it. And the exciting thing is that with just variability, you can get to 95% completeness and 98% purity. Of course, there is always trade-off. You can go to 100% completeness if you move this limit down there. Then this comes down to about 80–85%, which is not what you want. You want clean sample. So you take a hit in 5% completeness, and you have almost perfect quasar sample. And that's why that's demonstration based on Sloan data, that with LSST you will actually get millions of quasars, even though you don't have spectroscopy. And this diagram shows that when you look at this variability selected sample, it's actually better than color selection that Sloan used. In these two redshift ranges, there is mixing of quasar locus with stellar locus, and Sloan has significant incompleteness. But when you select by variability, you don't care about that color mixing. And indeed, we discovered many new quasars using this method in Stripe 82 that Sloan did not find in the first attempt when selection was based on colors. So variability is even better than colors. And then you can also do interesting physics with this fit. This shows now, this is cut off, this is redshift, this is luminosity, no, this is black hole mass, let me double check. Yes, black hole mass here. And here we have luminosity. So what it shows is different quantities color-coded on this scale. This is amplitude of variability in this and this panel, and this is time scale of variability. So the first thing you learn is that amplitude does not depend on redshift. It's just a function of absolute magnitude. So that gives you hope that at high redshift we will get the same efficiency. And then if you now try to compare amplitude as a function of luminosity and black hole mass on the x-axis, you find that these lines of constant amplitude are almost parallel to these dashed lines, and these dashed lines are lines of constant Eddington factor. And because of this strong correlation with Eddington factor, one is led to believe that we are looking at some process that has to do with accretion disk instabilities, and indeed there are more detailed models. For example, Eric Agel and his students developed where they have whole accretion disk and then localized instabilities where you have avalanche effect and you have burst of radiation. And when you integrate that over the whole disk, they can reproduce all the results in these diagrams. So 10 years ago, we didn't know whether quasar variability was dominated by accretion disk instability or by many supernovae going off that used to be called Christmas tree model, or gravitational lensing along the line of sight towards quasar. Today, we are more or less certain that it must be accretion disk instability. Going back to our own galaxy, this is collage of some results from Sloan, based on Sloan observations in the Milky Way structure context. It all starts with this diagram, which is U minus G, G minus R, which allows you not only to separate quasars from stars, but this color measures effective temperature of stars, and they are mostly on main sequence. So effective temperature is the same more or less as luminosity. If you know luminosity, you can get distance to these stars, and then you can make pretty maps like this. And for blue stars, F and G stars that live in this region, once you fix effective temperature, then this x-axis, which is U minus G color, measures metallicity of these stars. And so you can make metallicity maps. And so this is, for example, metallicity map for our galaxy. This is Andromeda galaxy in the back, just to tell you roughly where Sloan observes. So it is, the old data would fit in this blue circle. With Sloan, we went out factor 10 to 100 further. And now we have millions of stars with excellent metallicity estimates. This shows example of counting stars. So again, this point corresponds to this point. Galactic center is here. These are counts of stars from Sloan in some color range, some fixed luminosity. This is the best fit model that has exponential distance and a power law halo. It looks to the eye just like the data. When you subtract these two images, you get residuals. You have a lot of structure probably remnants of merged galaxies that you discover using this massive statistical survey and this sophisticated fitting and then subtraction. And that's basically what we will do with LSST2, but to about 10 times further limit. At Sloan, we can go to 10 kiloparsecs with this method. Out to 100 kiloparsecs, we can only go with RL Lyrae, which are much more luminous, but they are also not as numerous. They are more luminous, but not as numerous. So there is only one RL Lyrae per 10,000 of these stars. And the more stars you have, the better resolution you have. So you really want to take main sequence stars and to go to this limit, roughly limit of Milky Way halo. For that you need deep data, and that's what LSST will enable. So today we can do main sequence stars in this circle, and we will go with LSST to 100 kiloparsecs, but we can do with RL Lyrae. With RL Lyrae from LSST, we'll go halfway to Andromeda Galaxy. If there are RL Lyrae in this dark space where we don't know of any stars today. But models, these are models, this is the same 100 kiloparsec. Models tell us that we should expect a lot of structure. And so if models are correct with LSST, we will be able to map this structure to exquisite detail. And let me now go to the last topic of time domain. So basically that comes in two flavors, changes in fluxes and changes in positions. Changes in positions, again, come in two flavors. Tiny changes of stars, called proper motions of stars, and very large changes of moving objects in solar system. And so in solar system, you can discover new asteroids. With LSST, we'll get few million, about 5 million new asteroids discovered. With LSST, it was only a few 100,000. But with Sloan, I'm sorry, with SDSS. And with SDSS, for the first time, we had huge samples of asteroids with measured colors. So we could construct diagrams like this. Here, this axis that you cannot see is major axis of their orbit, basically distance from the sun. Jupiter would be around here, Mars would be around there, Earth is there, and Sun is probably in the corner there. And this is basically distance from the orbital plane. This is sign of orbital inclination. So this is essentially cross-section through asteroid belt. These are Kirkwood gaps. And these colors are real colors measured by Sloan. They're basically colors of the rocks that these asteroids are made of. And you can see there are two basic types. Bluish ones are carbonaceous asteroids, and orange and green are silicate-based minerals, just like interstellar dust, silicates and carbon grains. And that was for the first time that it was demonstrated that these big clumps, like these guys, they are called asteroid families. These three are called Hirayama's families. He was a Japanese astronomer who proposed that there were remnants of collisions, that big asteroids collided and shattered into small pieces. And the implication is, if this is true, then these small pieces should all be made of the same stuff, either carbonaceous or silicate. When you look at colors of these clumps, they should have homogeneous color distribution. And so before we didn't have data to do so, with Sloan we demonstrated that these things are indeed homogeneous. And with LSST we will have about 10 times, maybe even more than 10 times larger sample. And we will also have time-resolved measurements, so we will be able to see how these colors vary with time. And there are weak indications that there is color variability in asteroids when you look at Sloan. It's at few percent level. The hypothesis is that asteroids are not homogeneous on their surface. They look more like Dalmatian dogs, like they have one color and then they have spots.
Question, is the reason the ecliptic is not well sampled just having to do with where Sloan looked?
Ecliptic?
The ecliptic right
No, it has to do with your projector.
Well, I can kind of see it in zero. You know,
I'm not following you.
There's less data, zero.
Oh, here?
Right. Maybe it's more
Maybe a little bit
how
because
big.
families are never, these are inclinations, so
Yeah.
it's not really that they are not on ecliptic. This is angle between ecliptic and the orbit. So it's
Right.
distributed. And so zero means it's perfectly aligned with the ecliptic.
Right.
But ecliptic is just defined by Earth, so this
Sure.
is just one orbit out of many.
Sure.
So then, yeah. Oh, I thought you asked why is it missing?
No,
I
no,
misunderstood
I-
the question. So it's not the projector, it's. And then another big thing used to be much more important, not anymore, that Congress now is not giving any new signals, but Congress was very excited after September 11 about protecting US citizens from all possible bad things, from terrorists to bad asteroids. And so there was this mandate to NASA that they need to catalog all dangerous asteroids. And LSST is the only ground-based survey that can get to this completeness level. But recently we didn't get any signals that this would be still actual, and NASA didn't get any money, more importantly. So, but we will still look for these objects automatically, and we will try to get as complete a catalog as we can. Another time domain exciting thing is to do analysis like summarized here. This is from Matcha survey. This is science image around LMC region, and there is template image that looks to the eye just like that one, so I didn't even show it. When you subtract the two, that's the difference. There are giant circles on the sky. And so if you now go back to this image, you can trace with your eye some of these arcs. If I told you there are circles in this image, you would say I'm crazy. But now you can see definitely they are there, and that's basically because there was supernova explosion in the center. And these photons now reflect off probably dust grains, some kind of scattering of photons that were emitted there, and now you can see them as this concentric circle going through interstellar medium. And this kind of analysis will be done automatically by LSST. So when we do different images, we will get these automatically within 60 seconds. Not only pretty image, but measurements of everything that we find in these images. And then it's not obvious how will you search catalog parameters to recognize these circles, but there are ways to do it with machine learning and data mining methods. And then there is a whole other set of science you can do with LSST that LSST is not designed per se for, but it will be super useful instruments to have, like for example combining to other wavelengths, other missions, space missions, or combining even with non-electromagnetic missions like LIGO survey. They will have huge error bars on any signal that they detect. And that error bar is roughly of the same order of size as LSST field of view. So together it will be great synergy, and also it will be very hard to do it with any other telescope but LSST because of this large error bar. You need to have large field of view. And so let me now go through one more science example. So I didn't emphasize the common theme to these two science examples, variability of quasars, and this one is that they rely on faint time domain. You couldn't do them before SDSS. With SDSS, it was demonstrated that you can do this science, very exciting science, learning physics of quasars with variability, and this one looking for dark matter signature Milky Way halo. And then the last common theme is that both were done by my graduate students, so that's why. So the first one was Chelsea McLeod, who is at US Naval Academy now, and this one is by Sarah Lobman, who is now at Michigan. So what this map summarizes is the distribution of stars. So this is the volume covered by SDSS, by main sequence stars. Galactic center is around here. We are sitting here. The color-coded map shows metallicity on this scale. So you can see gradient in metallicity going from disk stars all the way to low metallicity halo stars. And these three squares, that's the main point of these few slides. In each of these squares, all these stars were looked at, and their kinematics was determined using proper motions from comparing Sloan to Palomar Observatory Sky Survey, and also using radial velocity from Sloan spectroscopic survey. And their distribution of velocities shows two-dimensional Gaussian distribution. And orientation of that Gaussian is given by this red arrow. And these three arrows, they all point towards galactic center. The stars in each of these squares, they know where the galactic center is. How do they know that? They know that because they're moving in gravitational potential that is centered on the galactic center. And the fact that these vectors point towards galactic center as opposed in cylindrical coordinates pointing this way shows that this potential is also roughly spherically symmetric. And it gives you constraint on the distribution of matter that produces gravitational potential, which includes both visible matter and dark matter. And so how do you now go from these measurements to constraint on potential? It's something called Jeans equations. It's basically integrated low-order moments of Boltzmann equation. If you understand these words, then you're in good shape. If you don't, you need to take class in galaxy dynamics. But basically, it's just standard method that connects force in which objects move to their kinematics. Ideally, If we could measure acceleration of stars, then it would be a piece of cake. F equals ma. You measure acceleration, you get force. From force you get potential, you know gravitational potential. But we cannot measure acceleration of stars, except for those handful in galactic center. For these stars, there is no way you'll ever measure the acceleration. But you can look at them statistically, just like when you do thermodynamics of gas in this room. This is essentially the same approach. And by measuring kinematics, all these velocity dispersions and everything else, you evaluate this left-hand side, which is abbreviation for gradient of gravitational potential. So you have two maps, two-dimensional maps. Along this axis, this is the same as rotation curves of galaxies that told us first time there was dark matter. This is now taking rotation curve of galaxies and extending it to two-dimensional analysis. And that's exciting because not only it's in our galaxy and not some other galaxy, but it's exciting because now you can get from two-dimensional constraint, you can get information about two-dimensional distribution of dark matter. Is it spherical, or is it squished, or is it prolate? We couldn't measure this before, and now you can do it with this sample. And so, of course, if you go through derivation of Jeans equations, there are some assumptions like it's a pretty galaxy, it's an axially symmetric galaxy, there is no structure, it's idealized. And then you wouldn't take it straight and say, I measure dark matter in real galaxy without testing it. So we tested it, Sarah tested it by taking very sophisticated n-body model of Milky Way. And so then she said, I know in this model what is true potential. Let me now try to get it through Jeans equations. And so basically, this is from Jeans equations, and this is ratio to the truth. Green means 1, so she does recover potential on artificial galaxy where we know the answer. And then she applies it to SDSS, and it looks just like this one. And then we need to interpret it. And so again, she runs Milky Way-like model, and she throws out dark matter. She just takes potential from visible matter, and she gets large discrepancies. She finds that acceleration that she measures is much stronger in this corner here than you can explain with baryons in the disk. If she puts dark matter in, she then has perfect explanation of measurements from Sloan. So almost directly, it's still indirect, but almost directly she finds evidence for dark matter. And furthermore, because there is two-dimensional constraint, there are two different axes that she can then constrain. And in both of them, she gets good description. This is histogram of residuals roughly centered on 1. She can then measure the axis ratio, and she finds that dark matter distribution seems to be squished. In order to explain kinematics of stars or in SDSS, with assumption of some self-similar ellipsoidal distribution of dark matter, that ellipsoid has to have axis ratios of 1 to 2. That's the bottom line statement.
Rule out triaxiality something with this?
Not yet. To really do a good job, you need to have this method that is now called here, you can't see it, it's called Van der Marel method. Assume self-similar ellipsoid. To do a good job, you really need to look at n-body models that were generated with different initial conditions. So sometimes they have triaxial dark matter, sometimes they have prolate, sometimes oblate. It's very expensive to do them. We estimated we need about 100 of them. And so far, over last year, we managed to get 5 or so. So we need to change something, get more computers, more people interested, something along those lines to do statistically robust job. This is a little bit of hand waving to say that it's still similar, but it's the first ever constraint, so it's still interesting.
Yes, what does that imply for, sorry, I don't want to get too far off the subject, for, I mean, how the dark matter would align itself? I mean, is there a reason you would expect it to be able to?
When you look at this limited number of n-body models and some other studies that people did with different pieces of code, different assumptions, they claim that dark matter halo can be both oblate and prolate. It's not universally that oblate, that in disk-like galaxy you get oblate dark matter halo. Sometimes it's prolate. Sometimes it's aligned, sometimes it's not within of the order, if I remember correctly, don't quote me, but of the order 10 degrees scatter. So sometimes it's perfectly aligned, sometimes it's off. And it happens that in this galaxy, for our galaxy, we got 1 to 2. So I wouldn't think it's some fundamental physical thing that it's 1 to 2.
This 1 to 2 aligned with the disk.
As far as we can tell, it's aligned with this. Although if you ask me how much misalignment can you afford and still be consistent with the data? I don't know the answer because we don't have enough simulations to answer this, but it's definitely not 45 degrees. It's bigger than 0, so 10, 20, 15, I don't know. So that's one, that was my most exciting PhD student last year. So she graduated, she's now a doctor, and she measured this 1:2 ratio. And I'll end, I'm running out of time, in just a couple of pages. So one point that you could get from all these slides is that it's going to be giant data set, it will be complicated data set, and the question is how we will analyze this. Of course, Nick and I will not. We are too senior. And computers are developing too fast. But you guys will. You have to think about how you're going to do that 10 years from now and 12, 15 years from now. One way to think of the data set is that you have 10,000 dimensional space that is populated with 40 billion points. And now you want to draw some statistical conclusions about this distribution. You are not going to do that in Excel, that's for sure. You will be asking questions like clustering. If you think of just three-dimensional space, you will want to find if there are morphological features like this. You will want to assign them meaning, physical meaning, what statisticians call classification. And then you'll want to look for the most interesting objects that are usually outliers in some distribution. For example, when Sloan selected quasar candidates, there were outliers in UGG-R color diagram. There were 10,000 stars per each quasar, but they are all found in stellar locus. And those outliers, they were very interesting and targeted as quasars. So how do we teach our students to do such methods, and how do we scale up to LSST from methods that we have today for Sloan? And we started teaching Connolly and myself few classes at University of Washington, and one of the problems was to find a decent textbook. There are many good textbooks, but not a single textbook that looked just like we wanted it to look. So we decided to write our own textbook, and so that's my shameless advertisement. So it's coming out in a month, and if you rush, you can save 20 bucks. It's still on pre-order. And what's the real reason why I'm showing these slides is that there is lots of Python code to go with it. There are about 200 figures in this book. Each one demonstrates some statistical analysis, from most trivial ones like doing robust determination of axes of two-dimensional Gaussian to very complex machine learning methods or doing Markov chain Monte Carlo and so on. All that is encoded in this distribution. You can literally bitwise reproduce every figure from that book, including getting all the data. And data sets include Sloan, linear, many other surveys, and it's even so intelligent that if you want to make this figure for the first time, it will go look in your laptop if you have this data set. If you don't, it will download it automatically. When you do it for the second time, it will say, oh, you already done this, you have this data, I'm not going to waste your time downloading it again. So it's really a nice piece of tools. It's all in Python, and it's ready to go, and it has some great methods. So for students, I highly recommend it, and this piece is totally free. You don't have to buy a book. You just go to AstroML and download this stuff. This is one example. This is Sloan Great Wall. These are galaxies in SDSS spectroscopic sample. There are dots. Now you want somehow to translate this point distribution into continuum distribution. And these are now different methods. These are Gaussian mixture model. This is dendrogram for minimal spanning tree algorithm. This is data again. This is kernel density estimation, nearest neighbor Bayesian method with two numbers of neighbors and so on. This is all, you can first get this data set without much sweat, and then you can do all these sophisticated methods, including visualization, without much coding, and then adjust to your own science. So I will stop here. So this is going to be on test. You have to remember that LSST is deep survey. There is this paper you can learn more details about. It will have 40 billion objects. And this is from my website, the paraphrased JFK. When I got married to my wife in Croatia some years ago, the priest wanted to impress her, she's American, with Croatian hospitality. So he said at the end of the ceremony, do not ask what your spouse can do for you. Ask what you can do for your spouse. So then I changed it to this. But it was inspired by him trying to make JFK. Thank you very much.
More questions? Yeah, Steve.
So I have two sort of related questions. The first one is, if you're going to do all the processing in real time, is there a proprietary period or is the data public immediately? And my second question is, how will we as the public sort of get it? Because big SQL databases sort of break down in a couple of million entries. With 40 billion entries, it's going to be really, really hard to get the data, at least in meaningful numbers.
Excellent questions, both of them. So first question about proprietary data. There will be two flavors of data. There will be time domain data that we will report within 60 seconds. It will be totally public immediately. And the reason is that many of these will be transients that you have to catch right away, or you will not see them ever again. And so if we had proprietary period, we would kill a lot of interesting science. So we could in principle then throttle IPs or something like that, but this will not be done. It will go to everyone in the world. Then there is second type of data, and that is yearly data releases. And that will be just like SDSS. You have to spend some time analyzing them, doing QA, establishing that it's robust enough to be released to the whole world. That part will be, we don't like to call it proprietary period, it's quality assurance period. And that will be released as soon as we know it's not complete disaster. It will be released to Chilean and American and US communities and some international partners. And after some period, TBD, between 1 and 2 years, it will go fully public. Before then, there will be some educational resources like JPEG images that will not be good enough for real science, but good enough for EPO. They will also go public earlier. And then second question was, how do you now handle billions of objects with SQL databases? That's another big difference compared to Sloan. With Sloan, the traffic, the data flow was one way, from the database to you, and that's it. With LSST, we are designing a system where you will be able to upload your code to the database and do some analysis on that database, and then only get the outputs that are interesting, like Y versus X plot for update. And so then, if you have to touch every single pixel, we are hoping that standard outputs will enable most of science. But we are cognizant that there will be some science that you want to go back to each pixel and maybe fit some different galaxy model or tidal streams that we will not do. So in this case, you would upload your code, you would have some automatic time allocation that would allow you to process few percent of data or 1%, whatever. You will establish my code runs, I'm getting outputs, they look like I want, it's great science, I want to do now the whole database. Then you would apply for time, you would apply for time allocation on the telescope, you will apply for time allocation on the computer system, and then there will be some committee, external committee, which will say, I really love what you calculate, but what he is calculating is not of great value, so we'll give time to you. That's how we envision it to work.
Rather than fighting for telescope time, we're fighting for server time.
That's right. There was one question in the back and then Tim.
Darren, just a lot of the things you showed, I mean, I think you're right that the efficiency of LSST for identifying interesting objects will be much larger than SDSS. But aren't you still confronted with the same issue for SDSS, which is, as far as I could ever tell, about half of the most interesting things that came from SDSS came from the imaging, but the other half came from spectroscopy. Are there any plans to try to cohere a spectroscopic program around LSST?
There are plans, but it's not part of the LSST project in the narrow sense of the word. So National Science Foundation, Department of Energy are funding well-defined set of deliverables called LSST that is just imaging. But for example, in May of this year in Tucson, there was a nice meeting where people from different communities discussed what could be or should be done with spectroscopy built on top of LSST data. They tried to assess how many resources, how much resources you would need to have. Then they tried to assess what we have today, nationally and worldwide, and then what we need to build to enable that stuff. So people are thinking about it, and I'm sure there will be some spectroscopic effort, but it's not part of the project in the narrow sense of the word.
Is there discussion ongoing within LSST about doing some sort of coherent spectroscopy as the imaging data is?
There is overlap between the two communities, but within the project in the WBS sense of NSF, it's not in our scope.
Maybe a good
Scientifically,
conversation
there
for
are people
lunch.
going to it, of course.
Good talk.
Yeah, that would be a good time, lunch conversation.
There are two keywords NSF keeps telling us: schedule, budget, schedule, budget, schedule.
Did you mention the schedule? I don't recall if you said when the first slide would be.
So yes, so within 1 year uncertainty, we should have first light with the big camera in 2018 or 19, and there will be smaller camera for testing that would come earlier. We should have as many pixels as DSS camera, for example. But there is 1 year uncertainty. We still don't know if we are starting next summer with federal construction or not, and that has to do with government shutdown and uncertainties with continuing resolution and so on.
Same telescope, just smaller camera.
Yes, in one raft. If you
Right.
remember rafts, it will be one raft.
I see.
Think and the question.
Yeah, so since this such a large field of view, I just worry about the astrometry precision, so how good it is.
Which precision?
And the astrometry.
Astrometric.
So there is absolute calibration and relative calibration. Absolute calibration drives only orbits of asteroids, and that we think we will do better than is needed. Because after you have many points on orbit, you forget about absolute accuracy, it just works out itself and cancels out. For relative precision, we care a lot about, because that will be proper motions for stars. It will also be some effects like differential chromatic refraction in atmosphere that will help us with quasars, and some other reasons. So we care a lot about astrometry. And so we think we will be able to reach, our requirement is to reach 10 milli-arc-second systematic error per one observation. And then when we take our coverage over 10 years, we get proper motions and so on. We get everything works out itself. So the key question is, are we going to get 10 milli-arc-seconds or not? And data from Subaru with some other telescopes show that we might get even to 5 milli-arc-seconds. So I'm not very worried that we would fail. And basically what we will do is we will first have rough astrometry kind of WCS level of 20, 30 milli-arc-seconds for all the objects. And then at the end, we will collect all the observations of the objects. So for a given star, or any object, we will have time series of these approximate astrometries. And then for each observation we will do recalibration of relative astrometry. So we will refit on this particular field astrometry for all the objects. And then for some objects like galaxies, we will know we must require they don't move. And then when you take all these observations of all the objects, we think that we will go way below this limit. So we will be truly limited by random errors of one astrometric observation to somewhere between 5 and 10 milli-arc-seconds, but systematics will be below that.
Last question.
So that means you'll be able to do parallaxes to
Yes.
a couple hundred parsecs, even on the face.
Well, depends, yeah. So it depends where you put threshold. But in that shorter version of that Astro PH posting, this one, there is a table that has parallax and trigonometric parallax and proper motion precision as a function of magnitude going from 20th magnitude to 24th. And it's of the order 1 milli-arc-second per year at the faint end. One more interesting thing to remember is that when you compare to Gaia, and there is a nice slide on Gaia, which I didn't put because I looked at profile of this department, and it was all those extragalactic people. So I had this beautiful diagram, I just removed it, I thought nobody would be interested. So this is showing photometric precision versus magnitude, R magnitude, this is 20, Sloan goes to here, LSST goes to the end of the lines. It shows proper motion, it shows parallax. And this is Gaia. Gaia, as you know, is dead at 20th magnitude. It doesn't transfer any data fainter than that. And of course, it's a space-based project, so it has amazing performance at the bright end. But at their faint end, they have the same performance as LSST. And then as you go fainter, it's basically, if you look at the two curves, like it was one system, like intelligent design. We have these two surveys. And so together, they will be very complementary and powerful for doing galactic structure studies. An easy way to remember what LSST will do is it will do as well as Gaia at the Gaia space end.
All right. Thanks, Zeljko, again.